In this section, we're learning how to use the central limit theorem to find normal distribution probabilities. Now, you should have learned how the central limit theorem applies through your lesson, and this will only demonstrate how to do this in the calculator. So, in the TI-84, the differences here in the TI-83, as always, is that there's a menuing system to do probability features and statistical features within the calculator. The function we're going to use, because we are finding normal distribution probabilities, we'd hit second in vars to get into the distribution menu, and we would still be using normal CDF. Now, when you pull up the normal CDF function, if you just press enter, it will tell you the 4 different inputs that it needs in order to come up with the probabilities. That's not any different if we're using the central limit theorem. The only thing that changes is that the standard deviation, it either needs to be calculated ahead of time or you need to enter it as an operation. I'll show you what I mean. I think entering it as an operation is the easiest thing. But let's look at an example problem. So the average speed of certain drivers, or the average speed of drivers on a certain stretch of the German Autobahn is 142 kilometers per hour with a standard deviation of 22 kilometers per hour. What is the probability that the average of 40 randomly selected drivers on this stretch is more than 150 kilometers per hour? Well, if you'll notice, there was no mention of a normal distribution here. But we're going to assume that we can work with the normally distributed set of data because the sample that we're drawing here is randomly selected, and it's a large enough sample based off the central limit theorem to guarantee that our sampling distribution would be normally distributed. So what we would do is just, based off of the fact that we're using a normally distributed set of data, just go ahead and sketch that out. The mean of this normally distributed set of data would be the same as the original mean of 142 kilometers per hour. The standard deviation of this one, because this is a sampling distribution rather than the original population, that gets affected. It is the original population standard deviation divided by the square root of the sample size, which is 40 in this case. So the mean of 142 is located, of course, in the center, and then the question being asked is, what is the probability that the average of 40 randomly selected drivers is more than 150 kilometers per hour? So 150 would be somewhere to the right of 142, and if we're looking for drivers that are driving more than this, we would need to shade to the right. All right, so that sets up our region that we want to find the area of, and that's what the normal CDF function will do for us. But in order to type this in, here's what we would do. So back to the calculator. The lower bound of that shaded region would be 150. And then the upper bound of that shaded region, I labeled it as positive infinity, but of course we'll use second, e, and 99, which just means 1 times 10 to the 99th power, so a very large number. The mean, so based off the given information, the mean was 142 kilometers per hour. We'll leave that alone. Then the standard deviation. It's not just 22 here, it's 22 divided by the square root of 40. We can either go off to the side and calculate that first and enter the result here, or, as I said, it's a little bit easier to do this in line. So that just means type in 22 divided by square root of 40. Now, it looks a bit weird that you're typing in a calculation as an input, but the calculator will know what you mean. It'll understand that you want to find 22 divided by the square root of 40 first, and then actually use that value within the normal CDF function. So it'll be fine. Come down to paste, press enter, enter once more, and it will calculate the probability for us. So 0.0107 is our final answer.